Thank you, Venkatesh. Hello, everybody. Yes, my slides are up. Thanks for joining us so straight after lunch. I hope I can keep your attention for a little bit of time. So who am I? I'm Brammert. I'm a data scientist at Booking. I've been Booking for about 3.5 years now, worked on a lot of things, have some hands-on experience building models, doing forecasting for our customer service. I've worked on personalization of our apps. And recently I joined the machine learning services track, which is a team or a track consists of multiple teams that tries to build tooling for all our data scientists to make their life easier and to scale machine learning at Booking. Right? So a few numbers about Booking before we start. So Booking is actually one of the largest travel e-commerce companies in the world. We have about 17,000 employees spread out in offices all over the world. A large part of that is actually customer service. We have about 10,000, 11,000 people manning the phones and emails to answer all your questions. We have about 150,000 destinations available worldwide. And every day we get more than 1.5 million room nights that are reserved on our platform, which means that as a data scientist, it's quite a nice company to work for because there's a lot of data coming in, a lot of things happening. So the outline of my talk is going to be the following. I'm briefly going to share how data science is organized at Booking. I'll talk about the machine learning pipeline, or how we see it, how we do it at Booking. I'll talk about how we do offline machine learning. How do we collect the data? How do we train our models? Then online model serving. How do we actually use those models in production on our website? A bit about model and feature monitoring and discoverability. And then I'll end up with some of the things that we still want to do and we want to work on. So let's start with data science at Booking. So we have a community of about 200 data scientists, and they're spread out all over the company, from customer service to front end to partner services, which is the part of the company that deals with the hotels and the bed and breakfast and all our partners. And we have economists, we have mathematicians, physicians, physicists, psychologists. So we have a lot of people with different needs, different expertises, and different preferred toolkits and methodologies. And we actually do not want to restrict anyone in terms of the tools that they want to and can use, so they can choose the tools that are the best for the question or the problem that they're trying to solve. But we do want to help them, right? We do want to build tools that everybody can use. So the mission of my track is to build tools that help scale machine learning across our organization. We do that by identifying what are common problems, what are things that everybody runs into, right? An example is historical feature reconstruction. Let's say you collect a data set of searches, and you want to enrich that with sort of more complex features, like how many bookings did someone make in the last 10 months? That's a feature that changes over time, so you need to sort of reconstruct that if you have an instance that's 2 months or 3 months old. You don't want to have the number of bookings that they made now at the moment that you create your data set, but the number of bookings that they made the moment that search happened. So we identify these problems, we then implement infrastructure and tooling to solve them, and we train and educate and consult our internal users, the data scientists and developers at Booking, on how to use these solutions. So how does the machine learning pipeline, or the general machine learning pipeline at Booking look like? Where I put general in quotes because this is how we do it. There's an offline world and an online world. The offline world is most of the time the realm of the data scientist. Whereas on the online world, you have to work together with developers to make sure that you can produce your models or productionize your models in a way that scales to the size of our traffic. And so you start with a problem formulation. You then try to get your basic training data, retrieve search instances, hotel visits, or hotel page visits, or anything else that you want to retrieve. You want to enrich these with registered features. You want to maybe transform them. And then you want to build your model using your preferred machine learning library, be it H2O, TensorFlow, or Vader, or something else. And then you go to the online world, right? There you need to make sure that all the features that you've put into your model are actually available online. You want to publish your model and your transformations, and preferably also your features, so that they're easily retrievable. You want to set up some real-time or batch prediction mode. And you want to, very importantly, also monitor both the output of your model and sort of the quality of the features that go in to be able to recognize when your model degrades or whether some feature suddenly goes missing because someone deleted it. So let's dive into the offline part in a little bit more detail. So our website itself runs on MySQL databases, but those are not really nice for sort of big data and for building big models, right? So we have a Hadoop cluster, or two Hadoop clusters actually, that store all our historical data, and in which we can do all our data munging and computations. And the data that comes in there is sort of raw JSON blobs, which are really nice because they're very extensible and very flexible. They're very not nice because it's expensive to parse them. And because they're very flexible, people can also easily remove things, right? So at the moment, it's all these raw JSON blobs, and we're actually moving towards having streams of data that are schema'd, that are checked, that are easily to monitor and easily to maintain. So then, once you have your raw data, you go into your data munging. We've built a tool that's called feature Vader, where Vader doesn't stand for the Star Wars Vader, but stands for Vader, which is a Dutch word that means father. So it's the father of all the features. You start with your instance retrieval, get your basic searches. You then do feature gathering. You sort of augment your data set with more complex features. You define your feature transformations, and then you go to modeling to build your model using H2O or any other library. Okay? So there's a few challenges that you have to work with. As I said, it's challenging to extract relevant data from the events. Right? They're big. We got billions of events every day, and you need to parse them all. You want to be able to do your feature engineering, right? You don't just want raw features like what's the check-in date of someone's reservation, but you want more complex things that maybe need aggregations over time, right? Then you need to do time coordinate matching because you have a data set that goes back in time. So you need to do these sort of timelines join. And you need to do that on data sets that are not hundreds of thousands, but hundreds of millions, maybe more than a billion rows of data. So that's also not a trivial problem to solve. But we built something in our team that's called feature Vader that we try to that we built to sort of solve some of these issues. It's a custom Spark ML transformer, and basically what it does is it takes a data set, a data frame, and it adds some columns to it. That's in essence what it does. So what you can do is you can create your set of instances. In this case, I'm not sure what it represents, but you have a user ID, some timestamp, and a label. You create a feature Vader object. You tell it, okay, this is the timestamp. I want features 1 and feature 2. And you simply feed the initial data frame through it, and you get your augmented set of features. A nice thing about this is that if someone sort of spends the time to define a complex feature, where it comes from, what the data sources are, right, then that can be reused by everybody else in the company. That's a bit the idea. Right? One person has to define and has to put the effort and work in defining the features, and the others people can consume them without too much effort. Right? Then you want to do feature transformations. Right? Raw features are generally not enough. You want to maybe normalize them, bucketize them, do a target encoder, do concatenations. So for that, we've also built some transformations on top of the Spark ML pipelines, with the added twist that you can actually save them in a way that's easy to use in production. Right? It's not just the saving where you store the state, but we store it in such a way that we can then use it in our model serving platform to quickly perform all these transformations online as well, without having to explain to a developer exactly how do I do my bucketing, or that you have to take this hash map and store it somewhere so you can retrieve it in production. And then for modeling, there's multiple libraries that we use, right? Webbit, which is an online machine learning library that basically feeds through the data one by one. So it's the complete opposite of H2O, right? It still deals with data that you can't put in memory, but it goes through things one by one in serial. Then there's H2O, of course, which nicely pulls everything into memory. You can run things on very large data sets. And there we have TensorFlow for creating neural networks. Right? At Booking, a lot of our data scientists, they use Spark. They use PySpark, to be exact. And for that, it's really nice that H2O has sparkling water, so we can actually use the best of both worlds. We can use the data munging capabilities of Spark, plus the model training of H2O without too much effort. Right? It's really easy to move back and forth. It scales to very large databases. You can do distributed training. And one thing that's very important for us at Booking, because of the way we set up our data sets or our data centers, is that there's an internal and an external backend mode. I think Kuba already mentioned it a little bit yesterday. If you have an internal node, the Spark session and your H2O cluster are integrally linked, right? You have one Spark node for each H2O node. But if one of them dies, then your H2O session is gone. You can't sort of recover from that because it's not built to recover, right? Which is nice if you have a cluster that's set up to protect that. But in Booking, we have something called preemption. So if a job comes in that has a higher priority, maybe some of your resources are taken away, right? And if that happens to be one of your H2O nodes, then you're done for. You can restart. So together with H2O, we actually developed, or they developed for us, the external cluster mode. So we can actually decouple our Spark session and our H2O cluster, do all our data munging in Spark, scale it up to as many executors that we want, and then sort of scale it down again and bring it to H2O to do the modeling. Right, online model serving. So the online world looks a little bit differently, and it's mostly the realm of the developer. Right? We have streams of data, Kafka streams to be exact, that enter our world and that we can consume both online using either feature mappers that are built on Spark Streaming or Kafka consumers that can then feed into like a Cassandra store, for example, so they're available online for quick retrieval. But we also feed them into our Hadoop clusters. And the nice, or not catch, but the nice thing about that is that by doing that, we make sure that the data on which we train our models and the data on which we actually score our models is exactly the same, provided that we make sure that all the transformations that we do are the same as well. Then we have a feature store that is basically a piece of Perl code, because Booking is built on Perl, that allows you to easily sort of collect all the features that you want. And that is sent to our model serving platform. So that's all sort of the realm of the developers. And the data scientists, what they have to do is they have to upload their model, maybe their transformations, into our model serving platform. And we can use it. Right? So again, there's some challenges. We want to be able to process these events in nearly real time. Right? We don't need it exactly at the same second that it happens, but we do want it to take only a few milliseconds to be able to process an event so we can use it in our models. We want to be able to have stateless and stateful transformations, right? If a search comes in and we see that someone is a certain country, all we have to do is register that. But if you have a feature that says, I want to see how many page views someone made, right, then we have to update a counter somewhere. So if you retrieve that counter, update it, and store it again so we can use it. We want a containerized infrastructure in which all of this runs so you can scale it up easily when traffic suddenly grows. And then you want to be able to serve all these things in near real time as well. You don't want people to wait for 2-3 seconds before they get their search results. You want them to get them, instantly, at least from their perspective. And so we have a model serving platform. It was built in-house, which supports several model types. So we have the H2O mojos, which are really nice because it allowed us to actually productionize things that go beyond a linear model. We have Bubble-Webbit. Well, Bubble-Webbit spits out linear models. We have TensorFlow and simple CSV files if you build a linear model in any other way. It allows both single and batch predictions, and it has, as I said, integration with live feature bindings. So how does it look like? One thing I haven't talked about yet, we have an MLS portal, so the machine learning services portal, which is a place where data scientists can go online and sort of upload their models, and also search models and search features. So what they do is they go to MLS, they say, well, I have a model, it's somewhere here in HDFS. Right, so you upload your model. It's being sent to our model serving platform where they load all the models in memory, so they're quickly accessible when you actually need to do the predictions. And at the moment that someone wants to make a prediction, they do an API call. Right? First, it goes to the feature store to augment the basic sort of context of the request with any complex features. It goes to the coordinator that sends it to a specific box. The box does the predictions and returns them, and you're done. Right? So as I said, we have a portal that we use to model but we use to allow people to upload their features and or upload their models. But it's also a place where people can search for models that have already been made, and a place where people can search for features that are already available, and they can see whether they're available online and offline. So I'm not sure if people can actually read this, right? But you can see it looks a little bit like this. We're constantly sort of designing and redesigning the interface. We provide monitoring as well, right? So you can look at, this is, for example, the output of one of our models, right? You show the distribution of the probabilities it spits out. And what you can do with that is you can see whether, well, something is off when your model is actually in production. It allows you also to see in which experiments your model is being used, in which places, right? So booking, any change that we make on the website goes through an experiment. So any place where a model is going to be used needs to be attached to the experiment. So you can always try to figure out, okay, I have a model, maybe some other people started using it, who are they, what are they doing with it? It allows for easy sort of discoverability of all these things. It also allows you to discover and reuse existing models, right? As I said, you can search for model names for people that build specific models. You can see, well, what type of model am I looking for? It allows you to see, again, also where they're being used. And it allows you to discover and reuse features. You can search for names of features, and you can see whether they're online and offline, who built the feature. And there we are already at the feature directions. Right, so I mentioned a lot of sort of building blocks, and I would be lying if I would say that they're all completely amazing and done already. We're still continuously developing them. You want to make the full pipeline smoother and faster so that it becomes really easy to build your model, add new features, evaluate it, and continue on. We want to limit the involvement of developers because they're a scarce resource, right? And a lot of the things that you need to do to productionize a machine learning model are maybe not necessarily very complex. They're tedious, but they need to be done. And some of these things can be automated away. An important thing there is actually automatic reconstruction of features online from offline. So the final goal that we want to achieve is you as a data scientist, you come up with a nice new feature that you've defined offline on your data set, where we make sure that the data set on which you define your feature is actually coming from a stream, so we know that the data is available online as well. And then take that definition of your feature and automatically create a definition for an online feature construction mechanism, be it a Kafka consumer, be it some sort of in-memory aggregation after you pull the data from Cassandra. But that's the final goal. So that's it. Thank you for joining my talk. Forgot to change that. This is slides from a previous talk I gave together with a colleague of mine. So we're hiring. You can find more information at working@booking.com or ping me and give me a message. That's it. I think we have room for some questions as well.
Yeah. If there are any questions, you can post it on Slido. I can see there is already one question on Slido. If you can.
I have to look there. What's the biggest, or rather the most important business challenge you've solved at Booking.com using H2O? Tell us more about the impact on H2O in the business. Well, I think the main selling point of H2O for us is the mojos. So the fact that it becomes really, really easy to productionize things that go beyond linear models. It allowed us to build more complex models that take more interactions with features and in that way sort of improve the accuracy of the models, simply because we had access to more complex models that we could use online. I think that's, at least for us, the biggest selling point for H2O. Any other questions? Can you give info on the hardware that you run your models and data prep? I can give a little bit of info just because I don't know much more than what I'm going to share. We have 2 on-premise clusters. They're both about 50K cores big. And they're shared between all the data scientists and product owners and everybody else that uses our data warehouse to search for data and to build our models. We have HDFS. On top of that, we run Hadoop. We also run Spark. Most of our data scientists run Spark to do all their model prepping and model training. How much data you have in bytes? I don't know. I know that if someone tries to run a query on more than one day of raw events, it kills the cluster. So we have a lot. Okay, a little bit more about Feature Store. Yes, so Feature Store is actually the name of the team that I'm in. So the idea of Feature Store is that it's the one-stop shop for all your features, both online and offline, where you define a feature, how to compute it. It then, the magic of Feature Store is the time-wise join. So you put a data set in with a timestamp, and it will reconstruct all the features for you in a scalable way, and in such a way that after you've reconstructed it, the next person that wants to use it needs to do a lot less computations to actually use the same feature. So it tries to democratize feature engineering, basically. How do you handle prediction failure of online models? That's a good question. It depends on what the failure is, right? If it's a failure because some of the data that goes in is missing, you have to fix that. If it's a prediction failure because your model degraded, because people change, behavior changes over time, then you have to retrain it. That's the only thing you can do. 200 data scientists. Wait, can you elaborate on devs being scarcer resources, or at least bottleneck rather than data scientists? Is it normal, opposite way around? Well, they're both scarce resources, I would say. But generally, our data scientists are embedded in teams of data scientists, developers, designers. And those teams do more than just use machine learning. So they have to divide their time between implementing a model for a data scientist and changing something in the back end so that a new copy can be shown, right? So in that respect, anything that we can do to take away time that a developer needs to do to use a machine learning model goes into time that they can then spend on other things or on changing things in a website that use the model. And I guess the last one, 200 data scientists, does that include data engineers, et cetera? No, it doesn't. It includes data scientists only. But the two flavors of data scientists that we have, namely people that answer business questions and people that build models that go into production.
All right, thank you very much, Brammert. Really appreciate your time. Thank you.